very happy to see so many faces here today. Thank you all for coming, and I will present my work, my thesis work, and I will start talking a bit about porous materials, and then I will give a short introduction to what aerogels are. So porous materials are materials that contains voids, such as this Swiss cheese right here. They are often characterized by their porosity, which is the volume fraction of voids. So porous material affects our quality of life, but mostly indirectly, as we don't work so much hands-on with these materials. But we can find them as thermal insulators in buildings, or adsorbents in wastewater treatment, or as catalysts in cars. But with the rapid advancement in nanotechnology, the usefulness of this material has expanded, in which functional properties can be mixed with high specific surface area. And this can lead to materials with a combination of properties such as low thermal conductivity or high optical transmittance. So aerogels are porous solids derived from gel-formed substrates in which the solvent is exchanged for air or gas. It can be prepared from a range of different precursors, in which silica is the most common, followed by organic polymers and carbon-based precursors. What they all have in common is that they are usually prepared from something called a sol-gel process, in which the precursors are hydrolyzed to form a colloidal suspensions, and these suspensions are then gelled via, for example, polymerization, cross-linking, or self-assembling. By removing the solvent, you can then form the aerogels. And the aerogels have certain requirements. Usually they have to be highly porous, which means they should be above that of 90% porosity, and they should be predominantly micro to mesoporous. So because of this sol-gel process, which often gives isotropic aerogels, and because of the fine porosity, these materials are usually very delicate. So one way to increase the strength is by aligning the material. But a quicker method is to use a material that already has what we call anisotropy. And wood is such material. Wood has a natural hierarchical three-dimensional structure and is composed of honeycomb-shaped cells that are aligned in the longitudinal direction of wood. And the wood cell wall is built up by three major constituents called cellulose, hemicellulose, and lignin. And the cellulose microfibrils can be found almost completely vertically oriented in the cell wall, giving strength and stiffness to wood. The most common route to prepare aerogels from wood is to extract the microfibrils and then build up the aerogel from nanoscale to the macro scale. And this is what is called a bottom-up approach. But since wood already has levels of porosity, their microfibrils are already highly aligned, we can instead shave off layers from wood and use it as nature gave it to us, which is a quicker method. And this is called a top-down approach. And this is what I focus on in my work. So the state-of-the-art top-down wood aerogels are mostly concerned with thermal insulation, in which their thermal conductivity can reach that of air. These are prepared by removing lignin and then removing hemicelluloses, which leads to rupturing of the wood cell wall. So the drawbacks of these materials are that they are highly macroporous, in which their pores can reach up to the millimeter scale. They can obtain low yield and low mechanical properties. And it's also questionable if they should be termed aerogels, since they're not really that nanoporous. So based on the work that has been done, we thought that we could improve on these structures. And this gave rise to the objectives of my work. So the objectives were to develop methodologies for wood nanostructural control towards fabrication and modification of anisotropic wood aerogels. It was to study the processing structure-property relationship, information of anisotropic wood aerogels, and to explore aerogel applications which benefits from these structural designs. So in a first attempt, we wanted to swell the cell wall to induce more porosity of the wood cell wall itself. However, this completely failed. Instead, we ended up with another structure in which we filled the lumen of wood with nanofibrillated networks. And this was a completely unexpected finding. But based on this finding, we could then build up a systematic protocol. So our protocol, how we propose it, is that you use a cellulose solvent in which you partially dissolve the cellulosic substance of the cell wall, and you diffuse out the cellulosic substance to the lumen space. You then add an anti-solvent to precipitate the cellulosic substance, in which you precipitate them, and we call these integrated aerogel structures. And the structural advantages with this is that you can improve the nanoporosity, but also you can retain the wood morphology itself. So I've divided up the work in 4 parts. The first part is the proof of concept of the integrated wood aerogel. The second is how to improve the structural control in formation of integrated aerogels. The third is to obtain shape memory aerogels, but also a little bit towards thermal insulation of these materials. And lastly, the design of integrated wood aerogels towards photovoltaic energy harvesting. So in the proof of concept, we formed the wood aerogel by treating native wood with delignification. This removes the lignin and opens up the cell wall, in which we could partially dissolve it using D-magnesium chloride at room temperature for 24 hours until the wood turns semi-transparent. We can then regenerate the wood, which is the same as precipitation, in acetone, and we can obtain the aerogel by drying it in freeze drying or critical point drying. Using scanning electron microscope, we could then study the structures in which we see that native wood and the lignified wood has the open honeycomb-shaped cells that are empty. But the lignified wood, we can see that they are slightly delaminated, and this is because we removed the intercellular lignin. The wood aerogel has a unique structure in which we have formed these lumen aerogels in them. Studying the specific surface area using nitrogen physisorption, we can see that the surface area rises a lot, both in the freeze-dried aerogel, but also in the critical point aerogel. And then we studied the cellulose crystallinity, in which we could see that when we remove amorphous lignin, the crystallinity increases, and then when we perform the aerogel treatment, the crystallinity decreases. But the crystallinity is still quite high, 63%, which means that we probably only dissolved a part of the cell wall. And we then studied the degree of orientation of the cellulose microfibrils inside the cell wall using 2D X-ray scattering, in which we perform an azimuthal integration over the strong 2O reflections. A value of 1 means that the microfibrils are completely isotropic, and 0 means completely anisotropic and isotropic. In which we see that the lignified wood loses a bit of orientation, and then the wood aerogel loses a bit more. But it's still very high degree of orientation, and this have benefits for mechanical performance. So we assessed the mechanical properties by performing longitudinal compression testing of these wood materials. And we assessed it by looking at something called the yield point, which is the intercept between the elastic region and the plateau region. Removing lignin removes much of the strength of wood, and then performing the aerogel treatment decreases the strength further. But when we compare this to bio-based aerogels and foams of the literature, we can see that this strength is quite unique. Black points are materials of anisotropic structural properties, and red points are for isotropic structural properties, in which we see that we are quite high at similar relative densities. So in summary of the first work, we obtained a novel aerogel structure through partial dissolution and regeneration using D-magnesium chloride. And by partly preserving parts of the cell wall and then forming these nanofibrillated networks inside the lumen, we could obtain a combination of high strength and high specific surface area. But there are limitations with using D-magnesium chloride. One is it's very moisture sensitive, which means that we need to add a lot of solvent exchange steps in order to remove water. The second is that if we treat it for longer, the wood piece will completely fall apart. So we cannot have good control over the lumen network formation. One way to solve this is by keeping a little bit of lignin inside the cell wall. But in order to dissolve cellulose, we need to change to another solvent. So in part 2, we tried to obtain better structural control information of integrated wood aerogels, and we use this ionic liquid. It's a guanidinium phosphorus-based ionic liquid. We prepared the aerogels by firstly delignifying them, and then we treated them in the partial dissolution using the IL mixed with DMSO in a ratio of 20 to 80 weight percent. We then heated it for 65 degrees Celsius and regenerated the wood in DI water and freeze-dried it using freeze-drying or dried it using freeze-drying or critical point drying. We started off our investigation by firstly doing different types of delignification and then treating it in the ionic liquid mixture, in which we saw that when we have high lignin inside the cell wall, which means low delignification times, we cannot form any networks in the structure. If we treat it for the 18-hour, the wood will start to swell a lot and eventually crack, which is not good. We found that a delignification time of 12 hours was a good middle point for structural integrity and this lumen network formation, in which we have about 3.5 weight percent of lignin still left in wood. So by using this 12-hour delignification, we could then treat it in the ionic liquid mixture for different times, in which we can develop the lumen nanofibrillated networks. And also, with treatment time, the cell wall itself becomes thinner as we are diffusing out the cellulosic substance. And at the highest treatment time, the 48 hours, we see that the lumen or the cell walls are very thin. And we have fibrils both inside and surrounding the wood fibers itself. We then studied the cellulose crystallinity. And what we see is already after 3 hours, most of the cellulose has become amorphous cellulose. And this signal does not change much over time. We then studied the degree of orientation, and we can see that already after the 3 first hours, we have lost most of the degree of orientation, and then it stays stable. But this is very peculiar because we know that between 6 and 24 hours, this is where our networks develop the most. So this led us to believe that the interaction with the cellulosic substance is very quick with ionic liquid. However, the out diffusion of the cellulosic substance to the lumen, that is probably the limiting step for this formation. In summary of this work, we developed a method for lumen structural network structural control by partial dissolution and regeneration. And we could see that we could use anionic liquid to dissolve cellulose, even though we had some lignin still present in the wood structure. We could control the wood swelling by preserving some lignin in the cell wall. And with this control, we could control the thickness of the cell walls and also the network formation in the lumen. So with our better understanding of how lignin is affecting the processing of this material, we thought to ourselves, perhaps we can skip the lignification altogether. So in part 3, we create lignin-retaining wood aerogels using the same ionic liquid system. But this time we take wood and we directly treat it using the partial dissolution in the ionic liquid mixture. But we raise the temperature to 85 degrees Celsius and keep it for 48 hours. We then regenerate the structure in water, and we end up with a structure with a high density of nanofibrillated networks in the lumen. And it seems like the cell walls itself only is comprising the compound middle lamella and the cell corners, which means the lignin-rich regions of wood. Studying the major constituents in wood, cellulose, hemicellulose, and lignin, we see that the relative content does not change much during this treatment. And this has a very strong effect on the physical properties. In the wet state, wood becomes very flexible, in which we can lock the shape by drying the wood. We can then return the shape by resubmerging it to water, in which we see that we have a shape memory function. We can further roll it and then lock it again. And if you see this video here, here's the response to water. And this is the first couple of minutes in water in which the shape comes back. And then keeping it a bit longer, it becomes even more flatter. But significantly is that we still can see that we have the flexibility left even after several cycles of this. So lignin is very important, this aspect. It provides structural integrity of the wood material, but also the adhesion between the fibers itself. So to better understand, or firstly, we wanted to look at the structure, the nanostructure, in which we see that even though we are twisting it and bending the material a lot, we're not inducing so much damage on the material. In which we see that these lumen aerogels, they are still present in the wood. And we could scale this by using larger veneers of wood, and we can make a helical structure, and we can also bend wood against its fiber direction. So to better understand the physical properties, we needed to study the cell wall chemical structure. And we did this by using confocal Raman spectroscopy, in which we used a multivariate approach. And we separated out the most different spectra. So I will start first with the lignin dominating spectra, which you see here. And what we see is that the cell corners and the compound mid lamella is very lignified. Then looking at the cellulosic signal, we can see that the cell walls are highly swollen and the lumen networks are also quite cellulosic. Separating out the hemicellulosic content, we can then see that the nanofibrillated networks in the lumen are very rich in hemicellulose. And then we can combine these signals and we see the effect more clearly. So to retain lignin inside the wood aerogel has some major effects for strength. So here we performed a longitudinal compression test once more, in which we can see that we can raise the strength about 4 times as much compared to the delignified wood aerogel. But one reason why it also becomes so strong is because the density increases a lot in this material. So having anisotropic structural properties can be a benefit for thermal insulation materials, in which we can obtain an anisotropic heat flow. This means that heat more easily travels in the direction of the material orientation. And we did this by measuring thermal conductivity. And the thermal conductivity is a sum of different contributions. Firstly, the conduction through the solid, through the gas, by natural or forced convection in the cells, but also radiation of photons. In our material, radiation and convection are highly suppressed. And since this is a highly porous material of up to 95% porosity, this means that the gas phase will be the dominating. And we can actually lower this contribution by having a shorter mean free path of air, which is the distance that air takes to collide into each other. So by having porosity, they can instead collide with the fibrils of our material. So by removing lignin from our material, we lower the density and enforce some nanoporosity in the cell wall, in which the thermal conductivity decreases in both directions. Then performing the ionic liquid treatment to form the delignified wood aerogel, we can further decrease the thermal conductivity. But this is quite interesting because we are still having the same amount of volume fraction of solids. As you can see that the density is fairly similar in both cases. This means that it's the structure change that we have enforced on the material that is leading to this lower thermal conductivity. We also see that the native wood aerogel obtains a lower thermal conductivity in the radial direction, but obtains a penalty in the axial direction. So in summary of this part is that we successfully fabricated lignin-rich integrated wood aerogel by selectively reassembling the cell wall, in which we could obtain high flexibility in the wet state, which also led to a shape memory effect as the wood could return to its original shape when we resubmitted it to water. We could also obtain lower thermal conductivity, both in the delignified wood aerogel, but also in the lignin-retaining wood aerogel. A big limitation with this material is that we are using organic solvents. Organic solvents are not very common in large industrial scale. We're also using a lab scale ionic liquid. So another way is we need to change to a more scalable solvent. And that's by using aqueous-based solvents. In part 4, we design integrated wood aerogels for hydrovoltaic energy harvesting. Here, we could directly treat wood via a one-step partial dissolution in aqueous sodium hydroxide at -6 degrees Celsius for 48 hours. We then regenerated it in water, and we formed what is called lumen hydrogels. And these hydrogels we did not have to dry. because the application is in the wet state. So this is a much more eco-friendly material, and it's way lower cost than our previous works. So if we first look into the morphology, we see that firstly we have native balsa wood. We then perform the hydrogel treatment, in which we form the lumen hydrogels. And then if we look at the relative content of hemicellulose, cellulose, and lignin, we can see that we have a decrease of the hemicellulose content, but overall it's fairly similar. We also see that the sodium hydroxide is affecting the chemical structure, in which we could obtain higher total charge in the hydrogel. We then studied the surface area, and we saw that we have a big rise in the specific surface area. And this can be better understood if you look into the nanostructure of the material. So if you compare the nanoporosity of the cell wall and the nanoporosity of the lumen fibrils, you can see that they are really nanoporous. And this is by far the most porous aerogel structures we have created so far. So before I talk about how we can measure potential and currents over wood, I have to give you some background into how it's even possible to obtain them. So if you place wood in water, due to capillary action, the water will rise in the material, and due to spontaneous evaporation that occurs at the top of the wood, the flow of water will be continuous. And wood has a net negative charge. This means that counterions will build up an electrical double layer on its cell walls. And they have two regions called the stern and the mobile diffuse region. So in this diffuse region, the counterions can slip, and this gives rise to something called a streaming current. And to counteract the short separation of the wood, a streaming potential is built up. And you can harvest this by putting current collectors at the bottom and at the top of the wood sample. So the current materials for this type of energy harvesting are usually concerned with porous carbon films, in which they can reach up to 1 volt in potential. But the limitation with these materials are that they have really low energy density, or current density. So in our measurement, we first started to measure the potential, in which we saw that native wood had about 10 millivolt of potential, and we could increase this potential about a tenfold using the hydrogels instead. We could then keep this potential constant over a long period of time. Here is 16 hours in water. And when we measure current, we can see a similar rise. And we could boost this performance, but instead of using water, we could use an electrolyte. So we increase the pH of the water bath using sodium hydroxide to pH 13.4. And then we could rise the potential up to 550 millivolts. And we also saw that the current showed a similar effect, in which we could go from the nanoscale, or to the from the nanoamps to the microamps. And this is quite high for these type of materials. However, this effect does not last indefinitely. It rather lasts for a couple of hours, in which you put wood into the electrolyte and ions will start to flow. And when the diffusion front reaches the top of the wood, this effect will level off and you reach a constant value. The neat thing with this is that we can recharge it by treating it in acid after we have done the alkali, and then treating it in water thoroughly to wash everything out. We can repeat this cycle. And we did this 11 times, in which we can see that we lose no performance over the cycling. So you can almost draw an analogy to rechargeable batteries here. And we can actually power practical devices using our wood material. So here we use the case with the alkali electrolyte, and we had 6 samples coupled in series. And firstly, we could power an LCD screen continuously. And we could then store the charge by coupling it to a capacitor, in which it took about 300 seconds to charge a capacitor of 1000 microfarads. So in summary, we produced an eco-friendly wood hydrogel in a one-step process using aqueous sodium hydroxide. We then saw that the wood hydrogel formation led to an improved hydrovoltaic effect, and it's likely because of the higher nanoporosity, the higher surface area, and the higher surface charge. We then saw that by using an alkali electrolyte, we can enhance the hydrovoltaic energy harvesting by enforcing an ion concentration gradient over wood. So throughout this project, we have managed to evolve this material. Firstly, in the proof of concept, we created an aerogel with a dual structure in which the lumen aerogels could give high surface area and the retained cell walls could give high strength. In the second work, we could obtain better nanostructural control by using an ionic liquid system in which we better understood the role of lignin, both in processing but also in its physical properties. And by controlling the swelling, we could control the structure formation. In the third work, we selectively reassembled the nanocomponents in which we could keep the lignin inside the cell walls, and we could completely eliminate the lignification. This led to flexible hydrogels in water, which then led to designer aerogels. And in the last work, we could perform a more sustainable preparation of the wood aerogels, and we could exclude all solvent exchanges, use a completely aqueous-based system, and we could perform this in a one-step process. But also very importantly, throughout this work, is that we managed to increase the material's yield. This means that we are using more of what nature gave us. And I think this is also an important aspect of working on natural materials. So the general conclusions of our work is that we developed methodologies to generate a unique wood structure in which we could control the lumen nanofibrillated networks, but also the thickness of the cell wall and create wood aerogels. And we did this by using dimagnesium chloride, an ionic liquid mixture, and an aqueous sodium hydroxide. We studied the processing structure relationships in which we could see that all our materials obtain high cellulose orientation, which gave a lot of strength to this material. We then understood the role better of lignin, both in processing, but also how it affects the physical properties. And through this nanostructural control, we could design materials for thermal insulation and for hydrovoltaic energy harvesting. And the last point, but very importantly, is that the diffusion of cell wall substance to the lumen was seen as a universal phenomenon in wood cell wall dissolution. So I would like to acknowledge some people. Firstly, I would like to acknowledge my main supervisor, Yuanyuan Li. I also want to thank my co-supervisor, Lars Berglund, all my collaborators that has worked effortlessly on all our projects. I would like to thank my group Biocomposite and all the people at WWSC and FPT. Thank you.